Welcome to all the participants to the afternoon session of the first day of this AICTE sponsored short-term training program. Our speaker for the afternoon session is Dr. Sumit Dare from IIIT Delhi. Welcome, sir.
Can you hear me?
Yes, sir.
Okay, thanks. Yeah.
I now request my colleague, Ms. Ramya, to introduce the guest speaker for this session. Over to you, Ramya.
Thank you, ma'am. Good afternoon to all. I feel immense happy to introduce our eminent guest, Dr. Sumit J. Dare. Sir is presently an associate professor in the Department of ECE at Indraprastha Institute of Information Technology, Delhi. Dr. Sumit received his Bachelor of Engineering degree in Electronics and Telecommunication Engineering from Pune University and PhD degree from the School of Computer Engineering, Nanyang Technological University, NTU, Singapore. Earlier, Sir was working as an assistant system engineer in Tata Consultancy Services, Pune, and was also a visiting research student at Massey University, Auckland, New Zealand. He worked as an intern at EADS Innovation Works for Airbus at Singapore and was pursuing postdoctoral research at the Commons Lab, UEB, France, for the project GRACE, that is Green Cognitive Radio for Energy Aware Wireless Communication Technologies Evolution. Dr. Sumit has been awarded Indian government's DST Inspire Faculty Award, which is a prestigious award for young researchers under 32 years age. His research interests include design and implementation of multi-standard wireless communication receivers, as well as application of machine learning algorithms and decision-making policies for various wireless communication applications. Sir has published more than 70 research publications, international journals and conferences. Also awarded Best Paper Award for IEEE conference and Young Scientist Paper Award for URSI conference at Canada. Sir, at this juncture, I welcome you once again to the portals of our institute, and we are indeed very happy to have you with us, sir. Hope all will have a cherishing time listening to Sir's lecture. Thank you once again. Over to you now.
Okay, thank you, Ramya, and thank you, Dr. Deepa, for inviting me again for the talk. So I'll just try to share the screen. I hope should not. Okay. Is it visible?
Yes, sir.
Yes, sir.
Okay, just 1 minute. I'll just reshare it again. So for audio one, I need to check some option, right? But that option is not visible.
It is not visible, sir. Include system or computer audio.
Yeah, that option is not there. That's what. So I need to do the open share tray screen
so when
share.
you share the screen, when you share screen, there will be a option include computer sound. When you share that, when you click on that itself, it will come, sir.
Okay, because at the below it is not there. Okay,
Otherwise,
let's
you
see.
can send us so that I can also. Can you?
Right now, I have just shared the screen, but let's see if that option is visible or not. I'm not sure. Let's try it. Okay.
Okay, sir.
So at least PowerPoint is visible, right?
Yes, sir.
Yes, yes. Sir, I have sent a snapshot of that option now to you.
Yeah, that option is there, but usually I am using the browser version, right? Because we don't use this Steam.
Okay,
so
okay.
I don't have the app. I think it is there in the application version, may not be there in the browser version.
Okay, okay.
Yeah.
So I have just sent a pic of that.
Yeah, Ramesh shared me, but I was a bit unsure about whether it's there in the browser one. Anyway, good afternoon, everyone. So I can start right now. Okay.
Please, sir. Please, sir. Yes,
yeah.
Sir.
Okay.
Thank you.
Yeah. Good afternoon, everyone. So in the today's talk, I think I have around 1.5 hours to 2 hours. I'll be discussing about the why we need to implement the algorithm on the edge devices. So when I talk about the edge devices, here edge devices are nothing but the devices which can be implemented on the remotely and without the need of continuous power supply. Means they can be battery operated, and also for processing you don't need to have the big laptop or a big CPU with them. They can work on the small microcontroller or small SoC. So we are going to discuss about those edge devices, and if you want to implement the algorithms on these edge devices, what are the platforms we have, and we'll take a simple example of these algorithms and we'll discuss how these algorithms can be mapped on the SoC. So before I start discussing about the technical work, I'll just briefly give us the background about the IIIT Delhi. Again, I'll try to play the video, but I'm not sure whether the audio will reach.
Imagine a place where students think beyond the books. A place where execution happens beyond the boundaries of what's known. Fulfilling a purpose not just now, today or tomorrow, but every single day. Dream of a mind so head on with the world. Unafraid to crave, pursue and design. So if you could create a better, a responsible you today and do the same tomorrow, what would you be? What would you do? Imagine. Imagine giving flight to the limitless dreams seen in the broad daylight, making them come true, one step at a time. Taking actions, executing, failing, learning, succeeding every single day, because that is who we are. Striving, thriving, taking actions in the moment. Only then, why becomes why not. Learning becomes fun. And your ambitions, your goals, your ideas, they just get closer with every tick of the clock. So much to do in just a day. Because at IIITD, we create responsibly. Indraprasth Institute of Information Technology, Delhi.
I'll skip that part. So IIIT Delhi, as you know, that it's a completely autonomous university compared to the other IIIT. It has a separate model. It's a completely autonomous, like IIIT Hyderabad one. It was established in around 2008, and we have the campus in the South Delhi, Ukla Phase 3. And on the website, you will see that we have well-maintained campus with all the facilities available. So the main focus of the IIIT Delhi is the research-based university, so where faculties are encouraged to focus more on the research, and the teaching comes along with the research part. So we have been well ranked even in the different rankings available in India as well as the outside. So being a 12 years old institute, we are doing quite well in the ranking. So if you want to know about the different programs and different curriculums at IIIT Delhi, feel free to visit the website. So we have mainly BTech program with the CS plus X model. So for example, we have the CS plus AI, CS plus computational biology, CS plus human-centered design, CS plus social sciences, and the electronics department at the BTech level. And similarly, we have the MTech program at the EC as well as the CSE department. And we have around PhD which is quite a big PhD program, about 150 plus, I think 200 plus research students now currently on campus. So even in the ranking based upon the publications, so you can see that there is one ranking which is based upon publications. We are ranking quite high. Being a research-based university, we focus quite high on the publications as well as patents and developing the prototype, which can be taken over by the industry for the product work. Our first director of the IIIT was Professor Pankaj Jalote. So he was the director for 10 years, and he read the book about how to build the research universities in India. So if you are interested in this domain, if you want to know about what is the difference between the research university and what are the challenges, feel free to read this book. It is available online, and you can purchase it, or you can ask your librarian to purchase this book. Okay, so now going back to the topic of the today's presentation. So here I'll be discussing about why we need to implement the algorithms on the architecture or edge devices. So we'll be discussing on the MAB algorithm, like multi-arm bandwidth algorithm. Then we'll discuss about what are the different system-on-chip platforms, how to make the architecture reconfigurables and the intelligent, why we need a reconfigurable and intelligent algorithms. And then we'll take the example of the MAB algorithms, and we'll discuss how they are mapped to the SOC. And then the regular performance analysis and the open research problem we'll discuss. So most of this work was done by my research intern. He is a BTech student and also working as a research intern in my lab, Sai. And the work is published in ISCAS 2020, TICAS 2, as well as OSCAS journals. And some work is under review in the IoT and the industrial electronics. So if you want to know more about this one, or if you want to replicate this work, we have the handouts and the source codes available on the GitHub. So if you are familiar with the SOC, Zinc SOC, FPGA, then you will be able to replicate this work. And if you want to have more details, technical details, you can look at our lab YouTube channel, where all is available. Okay. So in case you have any questions as of right now, feel free to ask me. I'll wait for 1 minute. So someone, Sudha, has raised the hand. So do you have any question?
Sudha ma'am, please post it on the chat, or you can unmute yourself and ask.
Or if anyone has any question, feel free to raise the question. Okay, so I will move to the first part of today's session. So the first thing I need to convince you that why we need to have the algorithms to architecture mapping. Like, why can't we just implement the algorithms at the data centers or at the GPUs which are there in your labs? And why that is not sufficient? What are the problems with those approach? Okay, so if you look at this plot, you can see that on the right hand side you have the year, and on the y-axis you have the market in billion US dollar. And if you see, something is growing exponentially on this axis. And if you look at this link, it shows that it's a cloud computing market, and you can see that the cloud computing market is exponentially increasing. And what are the reason behind this? You can see that there are a lot of IoT devices are being deployed everywhere, and they have also reached our homes also. So if you see the Alexa devices or the Google devices, all these are the IoT devices which sense some data, either your audio, video, or some environment sensors, and they send all these devices to the clouds. And that's why the amount of the cloud resources needed, or amount of the number of data centers we need to build, is the corresponding demand is exponentially growing. So we are being told that these devices are intelligent devices, but more or less these devices are basically sensing the data, and all the intelligence is happening at the cloud networks. So, for example, if you take a very simple example, suppose that you have the Alexa at your home, and you are sending the different queries to the Alexa, say 98 minutes per day. So only around 1.5 hours per day you are using the Alexa. Then if we consider 1 million people are having the Alexa, so you need to see that the in an entire day, the cloud needs to process 94 TB of data. So you need so many resources to process the data at the cloud, and also you need a network to so that this data can be communicated back and forth between the cloud and your device. Now the population is around 3.8 billion, and if we have so many IoT devices, then that means if you do the calculation with only 3 minutes per day, that means you are going to use the this device only 3 minutes per day, then you have to process the 11 picobytes of data. That's a huge amount of data. And with the work from home culture, we are going to stay more and more at our home, so we can see that this traffic is going to get increased. So also, if you see that in industry also, there is a lot of talk about the automations or the continuous monitoring of the machines in the name called Industry 4.0. That means more and more machines will be connected to the clouds, which means you need a more cloud resources and you need a more bandwidth to send the data back and forth between the cloud. So this is the one aspect where we discuss about the cloud resources as well as the data communication between the cloud and your devices. Another issue with the cloud-based processing is your green and the security aspects. For example, data centers consume significant amount of electricity due to the cooling requirement because of the all the servers, they need to be operated at a particular temperature which is significantly low. So you need a cooling requirement. Then you need to have the data redundancy. For example, you need to have store the same data at the multiple locations, so that if the one data center is down or one data center is under maintenance, you still can retrieve the data from the other location. Similarly, you need to meet the quality of service requirement. For example, if you are using the data for, say, a time critical application, for example, vehicular technology or medical one, you want to receive the data from the cloud within the certain latency constraint. So that means that data center should be located closer to the user. So these are the quality of service requirements are there, which means that you need to add the redundancy, or you need to build the multiple data centers. And it is expected that almost 20% of your electricity consumptions will be because of the data center by 2025. So you can see that the data centers need a considerable amount of the electricity, which means they are not green. So if you are interested in the design of these data centers, I'll recommend you to look at the Google, YouTube, Google, Facebook, and the Microsoft data centers. They have shared a lot of video tutorials about how they design the data centers, how their data centers are made energy efficient, either by designing it in the north region where the temperatures are low, or by reusing the sea waters, or by using the different techniques. So I'll recommend you to look into those videos available on the YouTube. So these are the green aspects of the data center, which means that we need to see how we can reduce the usage of the clouds. Second is, when you are doing the cloud-based processing, your data is taken out of your network, right? Your data is going to the data centers. So that means it is out of your network. That means it is susceptible to the various attacks. And all these devices are being designed so that they can collect a lot of information which can be used for some other purposes as well. For example, this information they collect, like audio samples they collect, can be used for training their algorithms so that they can perform better in the future. So these data are being used for other purposes which we are not aware about. You can see that there are a lot of news articles recently about how these data are being used by these companies for some other purposes. So that means, other than privacy, when the data is transferred outside your network, it is susceptible to the cyber attacks as well. Okay, and that's why the term edge computing, decentralized intelligence, edge AI, is being coined. And what is the main idea behind the edge computing or the edge AI? Is to distribute your signal processing or intelligence algorithms among the server, among the gateways, and among the units. So you don't have all the intelligence in the server or cloud. You distribute it here so that you can have the various kind of intelligence at the edge devices or at the gateway, which will not only make these devices more competent, also the amount of the bandwidth needed to communicate the data to the cloud can be reduced. Also, it will improve the security aspects. You can encrypt the data in better way so that the cyber attacks can be minimized. So that's where this edge computing and the edge AI term is being coined, and it is very useful, especially for the IoT devices where you have the large number of the sensors. Also, the same term is being coined in the wireless network, where you have the instead of all entire decision making is happening at the base station or mobile tower, how it can be distributed among the various units like small cell base station, picocell base station, or your mobile terminal. Even in the robotics, how each player or each robot can take that independent decision instead of all the decision making happening at the cloud, because when the decision making happens at the cloud, there will be some latency constraint, so which is not acceptable, especially in robotics and the medical application. So there is more and more focus on how to bring the algorithm processing at the edge level. Okay, so that's why there is a need of efficient implementation of the algorithms, which are signal processing, communication, or the AI algorithms on the edge platform. Okay, so I hope I have convinced you that there is a need of edge computing or moving the algorithms from your clouds to the edge devices. Now we are going to discuss about what are the platforms available in the market where you can map your algorithms on this platform. Okay, so if you have any questions till now, feel free to ask me. I'll wait for say half a minute.
Participants, if you have any queries, please post it.
Okay, so and now we'll discuss what are the platforms available for these edge devices or implementing, because when you want to implement some complex algorithm, you need to have the sufficient resources on the edge devices to implement that algorithm efficiently with the given power constraint as well as your latency constraint. So these platforms are usually referred as a system on chip platform. So you can see that the term indicates entire system is implemented on a one chip. Okay, that is called as a system on chip. So for example, if you see here on the left hand side, you will see the regular motherboard of a PC where you have the one PCB and the multiple chips. While the system on chip is nothing but the entire thing, all the functionality is implemented inside the chip. So you don't have the communication outside the chip. You don't have the multiple chips communicating with each other. So entire system is implemented in a SoC. So SoC is a single silicon chip that can be used to implement the functionality of your entire system rather than using the different physical chips on the board. Okay, so that's what we call it as a system on chip. So for example, if you look at your say any devices which has the Bluetooth connectivity, okay, for example, you can look at your headphone, which are the Bluetooth powered headphone. So to design the headphone, you can see that you can have a system where you have the one chip for the processor, and you have the another chip for the Bluetooth physical layer, and then you have this entire say headphone. Okay, but with the SoC, what you will have the single chip where you have the processor plus you have the Bluetooth. So what are the advantage? You can see that your size of the devices is getting narrower and smaller and smaller, your energy consumption, area requirement, cost, power consumption is going down. And that's why you can see that in our Bluetooth headphone, now if you look at the Bluetooth headphone over the last 10 years, initially we had the big headphone in the say 5 to 8 years back, and then we had this another set of headphones with some small wire in the neck region, and now we have those earbuds where you don't need any wires. Okay, so you can see that because of this SoC is one of the reason, but because of this SoC and you can integrate the so many functionality on a single chip, your size of the chip is going down, your power consumption, battery requirement is also, voltage requirement is going down, and since size is also going down, your cost is also going down. Okay, so that is the advantage of having this system on chip platform. So system on chip, you can get the higher performance because you can see that when you have the two algorithms inside a chip, your communication between the two algorithms is will take much less time than having the two algorithms implemented in two separate chips, because you need to, in case of the two separate chip, your data will be passed outside the chip, which will take the more time, and your capacitor, your wire will have more capacitance, so that will have the more delay. Also, the power consumption will be higher because you can see that when you want to drive the signal outside your chip, you need a more voltage than when you want to drive the signal inside the chip. So you get the better power efficiency. Then the footprint, as we have seen with the examples of your headphones, Bluetooth headphones or the mobile phones, your device size and weight is significantly reduced. And the reliability is high. Why the reliability is high? Because you can see that once you have the two Bluetooth and the processor inside the single chip, it will be very difficult for someone outside to look at the data which is being passed between the processor and the Bluetooth. Okay, you can't tap that signal externally. In case of the system on board, where you have one separate chip for the processor and one separate chip for the Bluetooth, there is a possibility that someone else can interfere with the signal passed between the processor and the Bluetooth chip. So that reliability is better, and you get a less interference and from the outside world. And also, as you are fabricating fewer number of chips, your cost will go down. Okay, and we can see these things in our real examples. For example, headphone, Bluetooth headphone, your mobile phones, you are getting more and more functionality with better energy efficiency, and also the cost is not significantly high. But what are the drawbacks of this SoC? Okay, so for example, they have the limited flexibility. For example, if you look at your laptop or PC, if you want to change the RAM, what you will do? You will just remove the 4 GB RAM and then replace it with the 8 GB RAM. Similarly, if you want to change the hard disk memory requirement, you will replace the new hard disk, because it's a system on board where everything is there as a separate chip. But in case of the system on chip, everything is there inside the chip. That is, your entire memory is there inside the chip. So it is very difficult for you to change the configuration once you manufacture or fabricated the chip. Most of the SoCs are designed for the applications desired application. For example, for Bluetooth headphone SoC can be used only for the Bluetooth. On the other hand, if you see your laptop, you can run the Bluetooth application, you can run any other application on your laptop because it's a general purpose laptop. Okay, but on the other hand, the SoCs are very application specific, and the complexities of the SoC design is significantly challenging, because you can see that in case of the system on board, you will have the separate manpower to take care of the processor, a separate manpower to take care of the Bluetooth, because both are physically separable. But now you need a designer who has the knowledge of the Bluetooth as well as SoC, because everything is being integrated on a single chip. Also, there will be a processor working at say 4 gigahertz, and then at the same time you have the Bluetooth working at say 1 gigahertz or less than say 1 gigahertz, or different units working at the different clock frequency. That means there will be an interference from one unit to another because of this change in the clock frequency. So there will be a possibility of interference. So you need to design your circuit efficiently to avoid that interference. So what is, to summarize, what you need is that you need a manpower who is well trained on this SoC design. Okay, so there is a significant switch between the skill set needed when someone is working on the system on board and when someone start working on system on board. So you need to make sure that you have the desired skill to manufacture the corresponding system on chip. Okay, so these are the main limitation of the SoC. However, this is not the end. We also need to understand that our consumer and the designer expectations are also changing over the time. For example, here consumer means the one who is going to buy your product, and designer means the one who is going to develop your product, or for example, any designer or architecture working in your company. So if you see over the years, so if you take the example of your mobile phones, and if you see the trend from the 2001 when the Nokia was the powerful company, to the 2020 when the Samsung and also many companies are there. And if you see the over the evolution over the last 20 years, you will see that every year we were getting the devices which are better in performance and which are better in terms of the integration. Means you are getting the devices which are smaller and smaller in size, and you are getting the performance better. Okay. So also, if you see the cost you are paying for, say, if you are paying the 10,000 rupees for a mobile with say X number of features today, and if you look at the say 10 years back, for 10,000 rupees, you will get significantly less number of features. Okay, so you can see that you are also not paying significantly higher cost, and also for those number of features which you have on the mobile today, your battery is still lasting for say entire day. Even if you see the 10 years back, though you had the very less number of features, your battery used to last only say one day or say around 1.5 days. So you over the years, our VLSI industries or the software industries were able to give us the product which are high, which are better, which are getting better and better in performance, as well as without compromising on your cost and the power consumption of your battery requirement. So these are the challenges which have been addressed efficiently. But now the things are changing. Okay, so now we assume that these things are available, the flexibility, the cost, power, integrations are available. But what we want is now we want the more flexibility and the scalability. For example, if you are a customer and if you want to say buy a mobile, and so someone tells you that okay, if you buy the today mobile, then you will get the mobile with the 4G capability. But after 1 or 2 years, when you buy a new when the Airtel or Jio comes with the 5G, you will have to buy a new mobile. So that is not a flexible architecture, because in the flexible architecture, you should be able to switch from the 4G to 5G using the same mobile terminal. Why you need to buy a new mobile terminal? So what consumer is telling that now you should design the equipment which are more flexible. So I don't need to buy a new equipment every time there is a shift in the technology. For example, when you purchase an app, and when there are some upgradation in the app, you don't need to buy a new app, right? Or you don't need to change your devices, because the upgradation of the app has been done at the software level, and at the software you get a lot of flexibility that by changing the code you can change the corresponding, you can upgrade your app. But such flexibility is not possible at the hardware level. So there is a need to design the hardware which is flexible. Also, there is a need of developing the architecture which is scalable. For example, if you are a design engineer and you are developing say you are working for a company which is developing two types of mobile phone. One mobile phone is for say low end, say low cost, and another mobile is a high cost, high end device. Now, suppose your manager told you that okay, for this low end devices, you should use some X processor from say one company, and for high end devices, you should use the Y processor for say another company. Now, as a designer, if you are working on a particular algorithm, then to make sure that your algorithm works efficiently on both the devices, then you need to study the architecture of the processor of both the devices. Okay, that means you have to do double the task, because you have to study the processor for the architecture of the low end processor and architecture for the high end processor. So what the designers are expecting, they expect that we should have the scalable architecture. So what do you mean by scalable architecture? That the same architecture can be used for the low-end device, and the same architecture can be used for the high-end device. Only the number of features will change. Okay. For example, if the low-end device you will have X number of features, in the high-end device you will have say 2X number of features, but the architecture will remain the same. For example, low-end device will have the single core architecture, high-end device will have the quad core architecture. Low-end device will have 30 kilobyte of cache memory, high-end device will have say 128 kilobyte of cache memory. So, but the architecture remains the same. So there is a need in the future now that people are expecting, the consumers are expecting the flexible architecture, and the designers are expecting the scalable architecture. And there has been a lot of various architectures are being developed over the last 20-25 years. For example, we had the simple processor based chip, then we had the processor and the GPU on a single chip, then we have processor GPU with the ASIC, which is used for the accelerating the dedicated applications. Then we had the FPGA, which is the field programmable gate array, which is used, which is on-field programmable, so you can dynamically change the functionality. So it is these are the two chip solution, because you have the two separate chips, one for the processor, one for the FPGA. Then people went to the one chip solution, where on a single chip you have the processor as well as you have the ASIC or the FPGA. So here the processor is the PowerPC processor from the IBM. So this came around 2005 or around that period. Then you have this next version of this one, which is nothing but the all programmable SoC, where you have this dual core ARM processor and this FPGA on a single chip. Then it is extended to the multi-processor SoC. So here you can see that you have the quad core ARM processor, dual core real-time processor, you have the GPU, and you have the PL, which is the FPGA on a single chip. Okay. And recently there are other so these are mainly from the company called Xilinx, which is now being acquired by the AMD. Similarly, from the Intel, which acquired another FPGA company called Altera, they are also trying to build the FPGA based SoC, which consists of the processor and the FPGA on a single chip. So for the edge devices, there are multiple options are there. For example, from the ST Microelectronics, you have this ARM based SoC, where you have these are the chips which are designed dedicated for the AI run the AI application. Similarly, from the NVIDIA, you also have the chips system on chip, where on a single chip you have the processor and the ASIC and the GPU integrated together. So all these platforms are available for the edge devices. This RF SoC is the recent platform which is used for the wireless edge devices. So you can see that you have the wireless transmitter and the receiver inside the chip. So you don't need a separate analog front end. You have everything ADC, DSC inside the single chip. So these are the platforms are known as a heterogeneous all programmable SoC. Why they are called as a heterogeneous? Because you on a single chip, you have the processing system. Processors are the sequential system. So you have the processing system, and you have the FPGA, which are also programmable. So everything is programmable. the communication interconnects between the processor and the FPGA are also programmable. So they are called as a heterogeneous, all programmable. That is, everything is programmable anytime. And these are the system on chip. So it's only single chip. Okay. So these are the various platforms are available in the market. So if you are working on the edge devices, you might be using one such platform. Okay. So any doubt you have regarding the different SoC platforms? Okay. So if we take one such platform, which is say the Zinc platform, you can see that you have the dual core ARM processor here, you have the memory interface, and you have the peripheral interface. And then this is your blue one is your FPGA, and you have the AXI interface between the PS processing system, which is the ARM processor, and the FPGA. Okay. So when you have the algorithm, so suppose you are developing some algorithm and you want to implement this algorithm on this SoC. So what you need to do, you need to do the hardware software co-design. What do you mean by hardware software co-design? You need to decide which part of your algorithms needs to be implemented on the processor and which part of the algorithm will be implemented on the FPGA. So suppose this is your algorithm which has the so many tasks, say F1 to F6. So you need to see whether you want to which part of this F1, F2, F3, F4 to be implemented on the processing system, that is say ARM processor, or which one to be implemented on the FPGA. So you need to do the you need to try out the multiple configurations to get the best possible performance in terms of the resource utilization as well as the latency. Okay, so this hardware software co-design is a quite popular term which is used for implementing the any algorithms on the heterogeneous SoC. For example, if you take the example of say deep learning algorithms, in the deep learning algorithms you have the various layers, convolution layer, fully connected layers, and then you have the functions, ReLU, software. So you need to design which part of your algorithms will be implemented on the FPGA, which part of the algorithms will be implemented on the processor. For example, you may have the convolution operation, which is the can be implemented efficiently on the FPGA, while you may implement the fully connected layer on the processor. So depending upon your requirement of the latency, your requirement of your power consumption, and the available resources, you need to take a call about which part to be implemented on the PS and which part will be implemented on PL. There are different profiling tools are there which can help you to identify, okay, this part if you implement on the FPGA, you will get the better execution time. Or if this part, if you implement it along in the PS, you will get the, you will have the more, you can use your processor more efficiently, and you can use the smaller FPGA. So this is the hardware software co-design. But this is not the end, because here we are using the FPGA, and if you see the FPGA, the full form of the FPGA stands for the Field Programmable Gate Array. And what is this Field Programmable Gate Array? That means you can change the functionality of the FPGA in the real time. And if when I discuss about the requirement of the flexibility, for those applications where the flexibility is must, you will see that the FPGAs are getting more and more popular compared to the ASIC-based solution. For example, if you see here that I have the algorithms which have say F1, F2, F3, F4, F5, F6 functions. And among these one, I am not sure why my F2 can be F2.1, F2.2, F2.3, or F2.4. For example, if you say the computer vision application, you may have the one algorithm which works well in the day environment, and you may have one algorithm which will work well in the evening, and one algorithm in the night. So in the conventional, say, ASIC-based system, what you need to do, you need to implement all the 3 algorithms in a parallel, and you will be using only 1 algorithm at a time. But using the FPGA based system, what you will have only 1 block, and you will configure this block with the different algorithms. So the same block will be configured with the morning algorithms in the morning time. Same block will be configured with the evening algorithms in the evening time, and the same block will be configured with the night algorithms in the night time. So you can see that using the same area, I am implementing the 3 algorithms instead of implementing 3 algorithms in parallel. So you can see that my area consumption is going down. My power consumption is going down because I have only 1 algorithm active at a time instead of having 3 algorithms active at a time. So this is called as a dynamic partial reconfiguration property of the FPGA, and this is the main reason the FPGAs are getting more and more popular in the edge devices as well as in your data centers also. So you can see that you get the lower power consumption. You can instead of implementing on a big area, you can go for the smaller FPGA. So smaller FPGAs are more cheaper, and they are more cost efficient, so that you can get the you can get the lower cost of your product. Okay, so these are the advantage are there, and also you can see that you are getting feature richness and upgradability. For example, today you gave your product to the customer, and then you found out that okay, there is a bug in the algorithm. In the ASIC based one, what you need to do, you need to recall your product, you need to refabricate the entire chip, and then you need to deliver it to the customer. While in case of the FPGA based SoC, what is the advantage here is that you don't need to recall your product. You just need to send a new bit stream to the customer, and that once that bit stream is downloaded on your FPGA, your FPGA will start implementing the new algorithm. So you are providing the feature richness to the customer. Your customer will be happy because he knows that in addition to I'm getting the better performance, better area, I know that if I need some improvement in the future, it can be done easily and quickly. Also the upgradability. For example, if I develop the product today, I am developing as per my today's requirement, but I don't know what requirement comes in the future. Like suppose that the future customer comes up with another requirement. Then what I need to do, I just need to develop the algorithms, map it on the FPGA, and send the new bit stream to the customer, and that algorithm will start working on your product. So you are giving the upgradability to the customer, that even in the future, the product can be modified to meet the new requirement. And these are the reasons your FPGAs are getting popular. And if you see in the wireless communications or the cloud, even in the clouds, or if you see the autonomous driving systems, everywhere the FPGAs or these SoCs are being used in that today. Okay, and this is, we call it as a reconfigurable architecture. But this is not the end, because even if you develop the reconfigurable architecture, for example, you develop the algorithm architecture which can switch between the 3 say algorithms, but you also need to decide at what time you need to switch, when you need to how you need to switch, and which algorithm you need to switch. So that means you need an intelligence. What is this intelligence? This intelligence will learn from the environment and then decide which algorithm to be used at what time. And such architecture is called as a intelligent reconfigurable architecture. So architecture is reconfigurable. That means it is able to switch between the algorithms, and it is intelligent because it is switching is not manual. Switching is that it learns from the environment, takes the decision, and based upon that it selects the algorithm which is best for the given environment. Okay, so this is called as an intelligent reconfigurable architecture. So this kind of techniques can be used in various applications. For example, you can use it in the deep learning base, where you know that your filter weights or the size of the filter weight may not be fixed, or it depends upon the environment you are working on. Or you can use it in the wireless communication physical layer, where you have the say OFDM data modulation, and you know that the beam forming, where you know that depending upon the environment, my beam direction needs to be changed. Also, my depending upon the SNR, my modulation scheme, my filters weights, my window weights needs to be changed in the real time. So there you need to have this intelligent reconfigurable hardware software design. Okay, so I hope I have convinced you about the different SoC, and I convince you the need of the intelligent and the reconfigurable architecture. Okay, so now if you have any doubt, feel free to ask me. Then I'll discuss about we'll discuss about how to take one say simple algorithm and how to implement them on the SoC. I hope everybody is awake because it's afternoon session.
Sir?
Yeah.
So someone is.
Okay.
Sir, could you please explain what an edge device is, and could you give me an example for that?
Yeah. For example, you have the like any sensor network, any sensor which is deployed in the your wireless sensor network. That is the edge device. Like for example, you have the sensor which displays which sense the temperature and then send that temperature value to the say gateway or the cloud.
Sir, if there are say 100 sensors, then all these 100 sensors can be considered as edge device.
Yes.
Okay,
yes.
Sir. Okay, sir. Thank
So
you.
all the devices which are edge devices means they are at the end of your means that they sense the information and they send that information to someone to your network.
Okay, sir.
So they are at the edge of your network, so that's why they are called as the edge devices.
Okay, sir. Sir, actually, my doubt is if there are devices at the edge, there can be devices before the edge also, no?
Yes, yes. So that's why there is a gateway also.
Okay, sir.
So so if I show you the slide, the first slide, so you can see that here you have the cloud, then you have the gateway, and then you have the sensors and the devices.
Yes, yes.
So you can have the intelligence at the gateway as well as edge devices. You don't need to have the entire intelligence at the cloud.
Okay, sir. Okay.
For example, if you take the mobile cellular network, your entire intelligence is at the servers or the network which is at the say Jio network or the Airtel network, and there is a limited intelligence at the base station. So now how to add more intelligence at the mobile tower or base station? That is like moving from the server to these other devices.
Okay, sir. Okay, sir. Yeah, it's clearly understood. Thank you, sir.
Okay, so now what we'll do, we'll take one simple algorithm and we'll see how these algorithms can be implemented efficiently on the SoC devices. Okay, so we'll discuss this multi-arm bandwidth algorithms. These are we call it as a online machine learning algorithms or decision-making algorithms because these algorithms does not need any training. These algorithms can be deployed directly in the environment, and they can learn from the environment and take the decisions in based upon their learning in the past time. Okay. For example, if you look at the website advertising, so when you go to the particular website, you will see the different advertising on that website. So you will see that after some time, you will see that the website is the advertising are somehow related to you. Okay, the things which you like or the things which you are going to, there is a high probability that you are going to click on that website. Those websites appear. And how this is done? Because what happens that there is an algorithm behind one. It learns from how you are accessing the internet, how different things you are searching on the internet, and based upon that, it is learning your interest, and using those interests, the corresponding advertisement are being put on the web pages you serve, and then once you click on those advertisement, there is some revenue will be generated. Okay, so the aim of the algorithm is to identify your interest and then put those find out the advertisement which you are more likely click, and and if you click, the corresponding provider will generate some revenue. Okay, so this is the one applications where these algorithms are used. They are also used in the clinical trials. For example, you have the say 3 to 4 drugs, and you don't know which drug will be the efficient one. So what you do, you try out the multiple drugs or the multiple people over the time, and then based upon the data you have gathered, you identify, okay, this is the best drug for this kind of people. Okay, so this is there also these are kind of algorithms are being used. Then in case of the wireless network, suppose that you have the IoT sensor network. For example, in case of the LoRa, you have the 4 channels, and if you see in the LoRa, all the 4 channels are chosen randomly. So how about learning the propagation characteristics of those channels, and then selecting the channel where you will more likely get the successful communication? Okay, so there you can use this learning algorithm. Or for example, you have the multiple wireless sensor nodes, and then you have the limited bandwidth. So if both the nodes transfer their data at the same time on the same frequency, your data gets corrupted. So how to identify that, how to make sure that both the nodes do not collide? So there also these algorithms can be used. Okay, so there are large applications of these algorithms, and if you see this top conference like NIPS and AAAI, you will see that at least 3-4 papers are are there on developing these kind of algorithms. So we'll start with the simple algorithms, which is called as the UCB algorithms. Okay, so assume that I have the say 4 options, say A1, A2, A3, and A4. And if I give you the say 10 slots or 10 chances, okay, and I ask you that you find out which one is the best option. Okay, for example, you go to the casino, you have been given 4 machines. So your boss tells you that, okay, take this 1,000 rupees and spend this 1,000 rupees and tell me that which machine is the best machine, so that I can invest more money in that one. So what strategy you will follow? How you will find out, okay, this is the best machine? Any idea? Yes, any guess how to find out the best machine? So what I'll do it is that I'll first explore the machines so that I'll get some information about the machines, and then I'll keep on exploring the machine sufficient number of time so that I get the enough information about the machines, and then I'll slowly eliminate some of the suboptimal machines, and I'll focus on the best machine. Okay, so this is called as the exploration exploitation trade-off, because here what you need to do, you need to explore the machine sufficient number of times, and after you explore the machine, you need to exploit the best machine. Okay, so you should not spend your entire money in the casino on just exploring. You need to quickly explore all the machine, and then you need to quickly identify your best machine so that you can invest most of your money in that best machine so that you get the better reward. Okay, so for example, assume that I have the K machines, okay, and I have the N slots available to you. So I can run my experiment for the N time slot. What do you mean by N time slot? That every time slot I select the machine, I put some money, then I get the reward that whether I have I have gained the money or I have lost the money. So the feedback can be say 1 or 0. That 1 indicates that my money got double, 0 indicates that I have lost the money. So in each time slot, I select one machine, then I got the reward for that machine, which is 1 or 0. Then I update this parameter x and t. X indicate how much reward I have received till time n. So if I selected the machine, say some number of time, I'll keep on accumulating the total reward I have received over that machine. And t indicates total number of times I have selected the particular machine. Okay, so x indicate the total reward I have received over the machine, and t indicates the total time I have selected the machine. So x by t indicates the average reward I will receive over the machine, and ideally I should select the machine which has the highest reward. So what I do in the first k time slot, I select the each arm only once. Okay, that means because in the beginning I don't have any information, I go to the casino, I try every machine once. Okay, then after that I find out the quality factor for every machine, like how this machine is behaving, and this quality factor based upon my learn information. For example, x is my learn information, t is the number of times I have selected the machine, this alpha is the learning parameter, log n is the number of times my horizon size, and the t is the number of times I have selected the. So you can see that this factor is sum of the two factors. What one is this is the, you can say that the exploitation factor, and this is the exploration factor. So what is the exploration? Exploration means I have to select the machine, each machine sufficient number of time, and you can see that the t is at the bottom. When the t is small, what it indicates that that machine has not been selected sufficient number of times. That means I don't have enough information about that machine. So this factor will force me to select that machine. Okay, and this exploitation factor, what is this factor? This factor is the average reward of that machine. So this factor will, if this factor is very high, then I will select that machine as many times as possible. So these multi-arm bandit algorithms try to optimize this exploration and exploitation threshold using this quality factor calculation, and in each time slot you find out the quality factor, and then you select the machine which has the highest quality factor. So multi-arm bandit algorithms, they try to optimize the this exploration exploitation trade-off, and UCB, which is the upper confidence bound, is one such algorithm which optimizes this exploration exploitation trade-off. Okay, and it's a very popular algorithm. So there are various versions of the UCB, for example UCB-V. So in case of the UCB, we are learning only the mean reward, but we can also learn the mean as well as the variance of the reward. So there is a all other variations of the algorithm which are modified as per our requirement. Okay. So if I want to implement this algorithm, I can implement it directly in the processor. I can write a C code. I can implement in the processor. Okay, only the ARM processor. I don't use the FPGA. So what is the advantage I'll get? I'll get the flexibility. For example, by just changing the C code, I'll be able to change the algorithm. I'll be able to change the number of machines. I'll be able to change from the UCB to the UCB-V or any other algorithms. And even in the future, if the new algorithms comes, I'll be able to implement that algorithm. So that's the advantage of the software implementation or implementation on the processor. But the problem is the software implementation, it's a sequential implementation. Your processor works in the sequential fashion. It takes the instruction, it decodes the instruction, it executes the instruction, and so on. So the latency is very high in the software implementation. So what I do the software hardware co-design. So what I did, I implemented the algorithm between the software PS and the hardware PL. So you can see that this is the parameter initialization step, this is the quality factor calculation stage, and this is the ARM selection stage. So here I am implemented the algorithms with the UCB is equal to K is equal to 2 arms. Okay. So what are the advantage I'll get here? Because of this part, the quality factors of all the arms can be done in parallel. I'll get the better execution, better latency than my software implementation. Okay. So I can implement for the k is equal to 2 arms, k is equal to 3 arms, k is equal to 4 arms by using the dynamic partial reconfiguration. So whenever the number of machines are 2, I'll activate these 2. When the number of machines are 3, I'll activate these 3 and so. So this is called the reconfigurable UCB. So why stop at the reconfigurable UCB? I can make the reconfigurable MAB. What is the MAB? Here I can switch between the algorithms also. For example, in some cases, I need only the UCB algorithm, while in some cases, I need the UCB-V algorithm, I need a UCB-T algorithm. So instead of implementing all the 3 algorithms in parallel, I need to implement only one algorithm at a time. And by using the dynamic partial reconfiguration of the FPGA, I can switch between the algorithms. So this is called the reconfigurable MAB. Here, I am dynamically, I'll be able to switch between the algorithm. For example, for some environment, I use the UCB algorithm. For some environment, I use the UCB-V algorithm. So if you look at the if you look at the result, so if you see the implementation latency compared to the software implementation or the hardware implementation, you can see that you get the significant improvement in the latency of the hardware implementation. And why this latency improvement is happened? Because in the software it's a sequential one, while in the hardware I can find out the quality factor of all the machines in parallel, so I can get the significant improvement in the performance. Also, if you look at the resource utilization, if I use the ASIC based implementation, that means I have to implement all the 3 algorithms in parallel. But if I'm using the FPGA implementation, I need to implement only one algorithm at a time, and the same block of hardware can be switched between the 3 algorithms. So I get the significant improvement in the area consumption, and this improvement will increase as the number of arms are increased, because I'll be doing the k number of calculations in parallel. So another advantage of moving your algorithms from the software to the hardware is that you free up your processor. For example, if you are implementing if your edge device consists of the single core processor, that means ideally in the embedded system, you need to make sure that your processor is free as much as time. Also, when you implement any algorithms on the processor, it is limited, the implementation is limited by the word length of the processor. So for example, if you are using the 8-bit processor or 16-bit processor, you have to implement the algorithm on the 8-bit or the 16-bit arithmetic. But on the FPGA, you can choose your word length as per your requirement. You can choose floating point, you can put 16, 8, 9, 10, 11 to any word length you can select based upon your requirement. So that's the advantage of the hardware implementation. So here I'll show you that I have implemented the same UCB algorithm either using the floating point, which is the 32-bit, using the 27-bit fixed point, or 11-bit. And you will see that in all the cases, I'm getting the similar performance. Obviously, the floating point will perform better, but you can see that in all the cases, I was able to find the best arm. So you can see that I'm selecting the best arm. So here you can see that the best arm is 0.7, here the best arm is 0.8, and here the best arm is this third one. So you can see that I'm selecting the best arm in all the cases. Okay. So word length has not affected my functionality, but you can see that by using the 11-bit architecture or 27-bit architecture, I get the significant reduction in my area requirement. My LUT consumption, flip-flop consumption, my DSP utilization, multiplier utilization has significantly reduced. So what advantage of the hardware implementation is that you can choose the word length, you can optimize your area requirement significantly on the hardware, which is not possible in the software implementation. Okay, so these are the advantage of the hardware software co-design. Okay, so we also extended it further, where we implemented the reconfigurable and intelligent physical layer of wireless communication. So you can see that this is the transmitter, this is the receiver, and these are the wireless channel. And this is your UCB algorithm, and this UCB algorithm learns from the environment and selects the best wireless channels, and also it selects the appropriate modulation scheme. Okay, so by dynamically learning from the environment and selecting the best channel, which will give us the best propagation path, you will see that you will get the better throughput and you will get the less number of repetitions. So we have shown in our paper that we get the better throughput. You can see that this is our proposed method. We get the better throughput in all the cases and we get the less number of retransmission. Okay, so you can look at these results later whenever you get time, but if you are interested in this domain. But these are the advantage of the using the machine learning algorithms at the wireless physical layer. Okay, so you might think that, okay, this looks very simple. You just need to take the algorithms and write a Verilog and C codes and then implement it. But the things are not that simple. So if you see that most of the machine learning algorithms or most of the complex algorithms, they are they are based upon the optimization routines. And most of these optimization routines are not synthesizable. So as a designer, you need to modify your algorithms so that you remove those optimization routines and modify such that the algorithms is synthesizable. Okay. So for example, if I take the KL-UCB algorithm, this is another multi-amp bandwidth algorithm which perform better than the UCB algorithm which we discussed. But here you can see that the algorithm has this optimization function, and these optimization functions cannot be implemented on the SoC. So if you look at the performance, okay, you can see that the KL-UCB, which is shown in the blue color, always offered the better performance than the UCB. But the problem is that you cannot implement it on the hardware because it is not synthesizable because of the optimization. So what we did, we modified this UCB function, which is the optimization function, with some synthesizable function. You can see that we have this for loop and very simple operation, and we were able to implement it on the SoC. Okay, so as a designer, if you are working on the SoC design one, you need to understand the algorithm and you need to make sure that the algorithm is synthesizable. Or if you are the algorithm designer and if you want your algorithms to be useful in the practice, you need to make sure that your algorithms is feasible on the hardware. If you design the algorithm which is not feasible on the hardware, no one is going to use your algorithm. Understanding about this SoC platform, how the algorithms are implemented on the platform, is very useful even if you are algorithm designer, because it will give you the insight how the algorithms needs to be designed so that they are useful on the in practice. Okay. So when we compare the KL-UCB and UCB, you can see that the KL-UCB is a significantly complex implementation, and that's why you can see that I'll still prefer the UCB algorithm, because you can see that the KL-UCB, the execution time of the KL-UCB is very high. So to solve this problem, what we did, you can see that in the previous slide we show that the KL-UCB performed better, but the latency and the complexity is very high. So what we did, we developed the reconfigurable architecture. What do you mean by reconfigurable architecture? You can see that now here I'm switching between the KL-UCB and UCB algorithm. So what I did in the beginning, I used the KL-UCB algorithm to do the exploration fast. And once I identify the new arm, best arm, I switch to the UCB algorithm. So what are the advantages I will get? Because I'm using the KL-UCB only for short amount of time, I'll get the less execution time, better improvement time, execution time, and also my power consumption will be significantly less. So you can see that my red one is my UCB algorithm, blue is the KL-UCB algorithm, and the yellow one is the KL-UCB plus UCB, where in the beginning I'm using the KL-UCB and then I will be switching dynamically to the UCB algorithm. So you can see that I'm getting the performance same as the KL-UCB algorithm, and my execution time is significantly reduced. Okay, so I'm not compromising on performance, but my execution time is significantly reduced. So as a SoC designer, you need to understand the algorithms. You need to make sure that you understand your algorithms, and then you efficiently map your algorithms on the hardware. Okay, so these are the works which are involved in the mapping any algorithms on the SoC. If you are interested in the MAB algorithms, you can see that there are a lot of algorithms are there in the machine learning community, but most of them are not synthesizable. For example, there are algorithms which use the inbuilt beta function. So in the C or the MATLAB, beta is like beta function is like a one line of MATLAB code. But if you want to implement on the hardware, this is not synthesizable, and you need to modify the beta function to make it synthesizable. Similarly, there are multiple various variations of this bandit algorithm for the different applications which I discussed in the beginning, and most of them are not synthesizable. Also, you need to understand that one algorithm may not work in all the scenarios. For example, we discussed that we have the UCB, UCBV, UCBT. Then how to add the intelligence to select the algorithms for a given environment. That means you need to learn the type of environment, and you need to identify which algorithm will fit for this environment, and you need to select that algorithm. So you need to add the intelligence algorithm. And also you need to select the word length. For example, in some time you may see that for particular setting, this word length might be sufficient, but for some other setting, you need a better accuracy. So you need some other word length. So you need to have the intelligence to select the word length. So these are the problems we have even not worked on, and these are like open problems in this domain. Also, right now we assume that our machine statistics are same. For example, when you go to the casino, if you go for the entire year, the machines will behave same. But it's not true, right? Every after a certain time, the algorithms in the machine casino will be changed, because they don't want to lose the money. They will keep on changing the machine algorithm so that the probability of you winning is as less as possible. So this is called as a quasi-stationary environment, where your environment keeps on changing. So you need to detect that, okay, my environment is changed. So you need to forget your learn information, and you need to relearn the information. So you need to use the change detection algorithm for such cases. Okay. So to summarize, you can see that the developing the algorithm is a totally different thing, and mapping on the SOC is a totally different thing. And some people are usually scared about the hardware or the SOC, and they think that the hardware is hard, but it's not hard. It's a different thing. So you need to have the knowledge of algorithms, you need to have the knowledge of SOC architecture, and you need to have a good enough programming skills to map your algorithms on the hardware. So if you are the SOC designer, you need to have all these skills. If you are the algorithm designer, make sure you understand on which platform you are implementing your algorithms, and then design your algorithm so that it can be efficiently mapped. So I discussed about the MAB algorithm. The same case is true for the other domains. For example, we worked in the deep learning algorithm, mapping of the deep learning algorithms on the SOC, and the same techniques are being used: hardware, software, co-design, making the architecture reconfigurable, and then making the architecture intelligence. Then the same thing in the wireless communication layer, system also physical layer. You make your physical layer reconfigurable, and you make them intelligent. So you learn about the channel environment, you learn about the user location, and then modified your physical layer to get the best possible throughput or the energy efficiency. So here in this session, what we discuss about the SOC, how the multi-bandit algorithms works, how they can be mapped on the SOC, what are the different ways to map on the SOC, what are the challenges are there in the other kind of the MAB algorithms, and what are the open research problems. So if you have any doubt, feel free to ask me now. Otherwise, I'll give you the some more insight. I'll take the 5 to 10 minutes about the insight related to the other work and the resources available to work in this domain.
So,
yeah.
Can I? So, well, finding the quality factor, you first told we should do the exploration and then exploitation. But in the equation given, you mentioned exploitation to be done first and then exploitation.
No, it is done both together.
Okay, together.
So yeah,
okay,
because
so
they like if you go to that equation.
Yes, sir, previously.
So you can see the quality factor is based upon the both the factors. So initially you can see that this value, you don't have much information about this value. So in the beginning, this factor will be dominant because your t is small. Yes. Your t is small, and in the beginning your t is small and x is also 0 because you don't have any past information.
Okay, okay, sir.
So this will be small and this will be large. So this will be small and this will be large. So this will be small and this will be large. So this will be small and this will be large. So this will be small and this will be large. So this will be small and this will be large. So this will be small and this will be large. So this will be small and this will be large. So this will be small and this will be large. So this will be small and this will be large. So this will be small and this will be large. So this will be small and this will be large. So this will be small and this will be large. So this will be small and this will be large. So this will be small and this will be large. So this will be small and this will be large. So this will be small and this will be large. So this will be small and this will be large. So this will be small and this will be large. So this will be small and this will be large. So this will be small and this will be large. So this will be small and this will be large. So this will be small and this will be large. So this will be small and this will be large. So this will be small and this will be large. So this will be small and this will be large. So this will be small and this will be large. So this will be small and this will be large. So this will be small and this will be large after some time, what will happen? You will get this will be non-zero, and this will also increase. Once this increase, this will become smaller.
Okay, sir.
And since you are doing with the log n, and this alpha factor is between the 0.5 to 1, this becomes smaller and smaller, and this factor will become more and more dominant.
Okay, sir. Thank you, sir.
Okay, so if you want to know more about this area, so we have recently in the FormsNet conference, which is usually organized by the IISc, we have given the 3-hour tutorial on this domain, where we have discussed the algorithm design also, as well as the implementation. So it's the 3-hour tutorial is available on the YouTube. So feel free to watch that tutorial so that you will learn more about this domain. And you also learn about what are the open research problem in this domain. So that I have given the link, and I have also given the, so if you, this is the page of our YouTube channel, our lab, and you can see that the corresponding video is uploaded here. Okay, so this is for some, if you are interested in this domain. Then other research works which we work in this domain is, one is the we worked in the wireless communication, and we work with the demonstration using the USRP. So this is the test bed. So the multi-arm bandwidth algorithm which we discussed before, they have also been implemented in the real test bed, and they are also integrated with the real transmitter and receiver, and the performance analysis has been verified. And this work got the best demo award in the 2016. So I'll just show you the small video. I know that the audio is not, you are not able to hear, but at least you will see some of the part of this video. So this is the test bed where you have the transmitter at one end, you have the receiver at another end, and transmitter selects the base channel based upon the propagation delay, and the data is transmitted over that channel, and then the throughput is calculated, and ideally you should select the base channel as many times as possible. So that was the this demonstration. So you can have a look at it later if you are interested in this domain. Similarly, we have recently, last year, along with the University of Luxembourg, we have developed the test bed for the ultra-wideband sensing. So if you see in the 5G, now in the 5G, you have the dynamic spectrum sharing. Your mobile can operate in the licensed spectrum, unlicensed spectrum, as well as shared spectrum. So that means your mobile needs to identify the spectrum in the wideband one, and you need to utilize the spectrum efficiently. So here we have demonstrated this ultra-wideband sensing based upon the sub-Nyquist sampler, and you can see that this is the sparse antenna array. So sparse antenna array means here actually there are only 4 antenna, and you can see that there are gap here. So these are the virtual antenna. So using the 4 antenna, we are reconstructing the signal which might have been received using the 6 antenna. So using the less hardware, only hardware required for the 4 antenna, we are generating the signal equivalent of the 6 antenna. So this demo was presented in the IEEE 5G forum in the last year. So I'll just show you the glimpse of how the demonstration looks like. So this is the transmitter antenna. So these are the horn antennas which are used for the beam forming directional transmission, and this is a proper chamber so that you can avoid the reflections of your signal. And so you can see that these are the virtual antennas. There are 4 antennas, and then there are some gaps in between to generate the sparse antenna array. So this is the receiver. You can see that there are 3 USRPs at the receiver, along with the octo clock to generate the clock signal. 2 USRPs are used for the received signal, and one USRP used for the synchronization purpose. Okay, and here you can see that this is the signal transmission, and you can see that we are detecting the DOA of the signal, direction of arrival, as well as we are detecting the signal clearly. Okay, so this is the demonstration, which is again details are available on our YouTube page if you are interested in this domain. So this is another test bed which is used for the air to ground communication in the L band, which is around 900 megahertz band, where we are doing the transmitter and the receiver, and then there is an interference is there. And by using the filtered OFDM, so in the OFDM, if you use the filtering, you can get the better attenuation so that you can reduce the interference to the user. So there we have demonstrated this one. Okay, so yeah, these are the works which we are interested. So if you are interested in any of this domain, or if you want to take it forward, feel free to contact us. In addition, we have also made because of this online semester, we have made our courses available online. So especially how to develop the algorithms on the SoC, how to write a Verilog code or C++ code. So all the video tutorials are available. So we have many labs available on our YouTube channel, so you can make use of those labs in either in your teaching or for the self-learning purpose. So here is the example of the video games are being developed on the FPGA board. So here the student write the complete code on the Verilog. So this entire code is written in the Verilog, and then the video game is designed. So you can see that this is the ping pong game has been designed.
Sir, is this an online training or offline training?
So we conduct online also. I'll come to that one. And this is also this workshop was conducted offline for the non-IIIT participants.
Okay.
Yeah. So this was around 6-day workshop was there on the Verilog code. So this is completely implemented on the FPGA, and he is moving the bars using the switches and the push buttons available on the FPGA. And you can see that the ball speed is also changing after certain number of hits. So you will see that in my regular course, which is the digital hardware design, every student developed the games, and we have given all the videos of the various games. That there are 19 games, video games have been developed on the FPGA using the various sensors and all. So if you are interested or if you want to incorporate in your course, feel free to look at these videos. Also, in the COVID-19, we have modified all our hardware labs into the virtual labs. So now at IIIT Delhi, all our FPGA boards are connected to the network, and the student can access all the FPGA boards remotely by sitting at their home, and they can program the FPGA boards and they can see the output on their laptop directly. So this, because of the COVID, one of the challenge was how to create such labs, hardware labs in the online mode. But one option was to skip the lab, but we went one step forward and we developed the remote hardware setup, so that now all our student learning is happening in the online mode without same as what will in the physical mode. Okay. So again, if you are interested, if you know how to set up this one, feel free to contact us. Another program we are organizing in every summer is this VLSI Revisited program. So it's a 4 to 5 week program, and this is planned just before the placement session, where every week we cover the one important part of the VLSI. For example, first week we start with the analog domain. It's a 5 days. In the morning we have the 3 hours of the lecture, and in the evening we have the 2 hours of the hands-on session. Then on the next week we'll have the digital VLSI, again 3 hour morning on each day, and the evening 2 hour session. Then we have computer architecture, digital system design, and this year we are adding the RF circuit design. So this course is not only theory, but also you will be given the access to the tools, and you will be developing the system using the hands-on exercises. For example, in my digital system design course, we developed the complete image filtering using the Vivado and the Verilog writing, and also we developed the accelerator using the high-level synthesis in the 5 days. So if you are interested in this program, it's a 5 to 6 week program. You can either do it for you can register for the 1 of the week or 2 week, or for the entire duration based upon your interest and the availability. So last time we had almost 80 participants all over India, and this time we are targeting around 300 participants in the online mode. We had around 5 faculties who each one takes care of the different domain. So you can see that most of our faculties have almost 30-40 years. Some of the faculties are 30-40 years of experience in the IIT. Some are having the 20+ years of experience in the industry, and a few are the academicians like us who are also working with the industry. So this program is, I highly encourage you to share this information with your students, as well as with anyone who is wants to get more expertise in the VLSI domain, as we know that in India we have a significant job market in the VLSI. Okay, so this completes my talk for the today. So I'll be available for the question and answer sessions. If you have any questions, feel free to ask me now.
Participants, you can ask your queries. So one person previously, I think KCG 85, he was working on scheduling in sensor network. What suggestion would you give in this regard? Working on scheduling in sensor network. So
yes, scheduling. It's basically you need to avoid the collisions between the different users. So you need to make sure that all the users are orthogonalized in the time and the frequency. So you need to develop the algorithms in that case. The issue is that you have so many users. So how to schedule those, because you will have say 100 or 100 plus sensors. So that challenge is there. So you need to develop the algorithms to avoid the collision. So there are bandit algorithms are one of the algorithms, but there are other algorithms are also there. Conventional algorithms or reinforcement learning algorithms are also there in this domain.
Any other questions? Participants can unmute and then also ask. Okay, sir. So on behalf of the organizing team and all the participants, I would like to place my sincere thanks to Dr. Sumit sir for accepting our invitation in spite of your very busy schedule. Thank you so much, sir. I'm very sure your talk could definitely have been well received by all the participants, and we look forward for your continual support and association with us in future also. Thank you so much, sir.
Yeah, thanks Ramya, and thanks Dr. Deepa for the invitation.
So thank you, sir.
Thank you.
Thank you, sir.